Hello, I'm Gerard Canisius again with my second video in the StoBE series. StoBE stands for Small Things to Big Things in Engineering, where I use small scale models or small things in life to explain big things in engineering. Please subscribe to this channel and also leave likes and comments. If you press the all button, then you will be notified whenever I upload new videos. You may have seen my first video, the StoBE-1 on Corbelled Arches. This one is about semicircular arches, also called Roman arches, because although they existed long before the Romans, it is the Romans who perfected it and built many structures. Here I will present to you a fundamental property of a Roman arch, a behavior which is necessary for it to not collapse. As you will hear next, it is a property that makes the behavior of a Roman arch completely different from that of a Corbelled arch. Now, the behavior of a Corbelled arch is very different from that of a Roman arch. It's because, as you would have seen, the Corbelled arch was like this and it would collapse like that. The supports, the end supports, which are my elbows, will stay the same, but it can just collapse like this. Whereas one of the semicircular arches or any other arches like Gothic arches, they are like this. They won't collapse by just this falling down, but it can collapse if the two supports move apart like this. Then the structure collapses like that. So this is the difference between a Corbelled arch and a semicircular arch or a Roman arch. A Corbelled arch does not have what's called the arch action, where the two ends, which are called the springings of the arch, try to push the supports out like this. So that's the arch behavior, real arch behavior. Corbelled arch does not have it. It just collapses like this. You may recall that the stability of a Corbelled arch depended on the weight of the interlocking bricks or blocks that formed it. For a Roman arch, such weights are only an extra burden to carry. The two sides or the two parts of a Corbelled arch could collapse independently of each other. This independent collapse of the two sides cannot happen in a Roman arch. The Corbelled arch is called a false arch, whereas the Roman arch is called a true arch, because it's having this behavior where you need good supports to keep it up. That's the true arch. To demonstrate the behavior of a semicircular arch, I have some blocks kept here. They will give me my side support. Now, because these arches need very good supports, people will build big brick or stone or concrete abutments that can provide the required support, which will prevent the arch spreading out, as you will see in the demonstration. However, in the case of a series of arches, only the two end arches require sufficiently strong abutments. For example, as for this railway viaduct in Wales. This is the massive end abutment of the series of arches of this railway viaduct in London. This shows two rows of arches in a church in Petaluma, California. These are rows and rows of arches in the Mosque Cathedral in Cordoba in Spain. As you can see, these are double-decker arches. One day in the future, I will explain their significance. Now, this is an interesting structure, not because it is leaning, but because it has little arches going round the building in circles. This means they don't have end arches that require lateral support. Now, to demonstrate my Roman arch, I have little blocks of wood cut here. As you can see, they are wedge shaped. Not only wedge shaped, but they are truncated wedges where you cut them off. So when you want to build a semicircular arch, you will have either the stones or the bricks shaped like this and called voussoirs. However, for example, bricks with mortar are to be used, then there is no need for voussoirs because the mortar joints can create the required curved shape. This is the device I made to help me build arches for this demonstration. It is called centering. You build your arch on the centering. So we keep blocks along it or bricks, and then we lower the centering so that the arch can stand on its own. So let's start doing it. Now this last gap is filled by what is called the keystone. Something you will notice if you look at more ornamental arches, that this keystone is very nicely decorated, showing that it is the most important voussoir. But actually this one is not more important than the rest. They all play an equal part in keeping a structure up. It is like a chain with a lot of links. Not one link is more important than the other. All are important. If one link breaks, the whole thing breaks. Let me take the centering out. To do that, I take these little things out and lower the centering. In real life, when you do centering, you don't have a solid one like what I have here. For example, you see here a conjectured centering for the Pont du Gard in France. Pont du Gard is one of the famous Roman aqueducts. I took this photograph at the Pont du Gard Museum some years back. This one is staying up because of the support given by blocks. These three blocks and these three are just the platform, but it is these and these which give the required support. Now, what you will see is if I am to take these supports out, you will see this bottom of the arch moving sideways. Did you see? It moved a little bit. It moved and now it's staying up because of the friction provided by the wood. If I try to put a load up here, you will see this is going to move further. Can you see? I'm applying a force at the top, like a load, and this is moving sideways. So that's why I said an arch needs very good supports. Now, although these move like this, in a real arch, when this happens, there will be cracks, but brick and stone arches are very stable. Here I got distracted and let the arch move without its support. However, it provided unintended evidence of what I said, that a brick or stone arch is very stable. That's why it moved towards the support and then stopped. Not only stopped, but it did not collapse. Until out of my reflex action, I touched it. And now you saw how it went out. Let me put this back carefully. Don't fall down. Don't fall down. It fell down. Let me build again. To demonstrate this arch can take load, I'll keep these blocks on top. So I kept two of my spare voussoirs, and then if I want I can push this and it stays up. So that's how an arch works, where it needs these supports. Very different from a corbelled arch. Now an arch is very stable, because even if the supports give way a little bit, like I do here, right? the arch can lower a bit, like now there's a gap here. A gap can happen, which is like a crack in the structure, but the structure is still strong. Now you will remember the situation where the arch moved sideways, then came to a stop after reaching the support, and then stayed up without collapsing. It showed something very interesting, something that we learn at university but may not be lucky to see in real life. That is, an arch needs at least 4 so-called pins or hinges for it to collapse. A pin or a hinge is a location of the arch where the material has failed either by cracking or by crushing in compression to allow the two parts either side of it to rotate freely relative to each other. If it is only 3 pins that's present, then the structure will not collapse. In this picture, I have marked 3 locations where gaps had developed, creating 3 pins. Because this is a 3-pinned arch, it did not collapse. If the arch supports or the springings had moved further, then a 4th pin would have developed and the arch could have collapsed. Fortunately, in real life, the supports of arches don't move that far. This shows how when we keep on increasing the load on an arch, its springings will apply extra forces on the supports and displace them to create a 4-pinned arch that then collapses. And here, and it's collapsing. Yeah. In this frozen frame, within the blue ellipses, we can see the 4 pins that have formed. The fulcrums of those pins we can see inside the red circles. And the result is in this part I am going to show you that an arch which has cracks, or in our case gaps, can still take load. For this I am going to displace one of the supports so that one or more gaps are developed, and then I will load the structure. Then you will see how it can take load. Then when I keep on increasing the load, how it collapses. The load that it can take depends not only on the arch but more on the supports. As the load increases, the resistance required from the supports also goes up. At a certain stage, when the load is high, the support will get displaced and then the structure will collapse. You can see that it started with 4 pins, then one of them closed. Because of that, a new pin formed in the springing at the right support. Now I like to stress that an arch can fail in different ways depending on its construction, the loads on it, the foundation conditions, that is the support conditions, etc. These are called failure modes in engineering. In our case here, we considered only the failure mode of supports moving apart horizontally. In addition to moving apart, supports can settle differently. One side can go down more than the other, which is called differential settlement. That can have an effect on an arch, as you can see in this demonstration. I will remove each of the 3 blocks that support the arch on the right side to give it a differential settlement. We can see one pin here, second one here, it's developing, and the third one, which has become bigger. To increase the differential settlement, I will lift up the left support of the arch using a block. Even with this relatively significant differential settlement, the arch has still got only 3 pins. To study what can happen to this arch, let's move the right support horizontally like we used to do. This one is still big. This has I think increased in size, but this is closing a little bit, becoming like a 2-pinned arch now because of the change in the geometry. So this one has now completely closed. This one has become wider. This has become wider. From 3-pinned arch, it became a 2-pinned arch. Let's see what happens when I move further. What happens now? The pins shifted their location and it became a 4-pinned arch and collapsed. If the supports are very solid, then they can't move apart, an arch can fail and collapse in other ways. For example, depending on the loads applied, an arch can develop a fourth pin by the crushing of its material. Nevertheless, as I mentioned before, Roman arches are very stable. For example, in a well-designed and constructed Roman arch, it is not easy to create a fourth pin by the crushing of bricks or stone. Also, such an arch would not suffer relatively large displacements such as what we saw in my models earlier. Such an arch may suffer some cracks, but it would be able to support loads as required. I like to mention here that since the Industrial Revolution, also other materials have been used to build arches. For example, iron, steel, reinforced concrete, timber, etc. What you see here are two examples of covered timber road bridges in New Hampshire in the United States. These, built in the 19th century, have laminated timber arches. This is the wrought iron arch roof of the Paddington station in London, built by the great engineer Brunel. This is a very impressive railway viaduct by another great engineer, Eiffel of that tower's fame. This early reinforced concrete arch bridge in Mostar in Bosnia-Herzegovina was completed in 1913 and then reconstructed in 2004 due to heavy damage suffered during the Bosnian War. As steel does not crack in tension, and reinforced concrete, although can crack, would still resist tension because of the reinforcement inside it, they form pins differently to a masonry Roman arch. Interestingly, many such modern bridges have been built with 2 or 3 pins already incorporated into the structure. This is for engineering reasons that I hope to cover in a future video. Thank you very much for watching this video. If you liked it, please subscribe and provide your comments.